Saxon Algebra 2, Lesson 60. Welcome, students. We have a great, straightforward, one-topic lesson on something called direct and inverse variation. These can be physics problems, but they also are really natural, everyday life type problems. We're going to talk about direct first, and then we'll do a problem of direct, and then we'll do an inverse. All right, they're slightly different. The formulas look a little different, but we'll handle them as two different topics, but it's really one. Okay, have you ever hung out with toddlers or seen them in action? Yes, you have. Have you ever noticed that if toddlers walk into a clean room, they start grabbing toys off shelves, right? I don't know if you've ever worked in a nursery at church or been in a playroom with kids, but each child immediately starts pulling out toys, right? Imagine one child walks in and he just starts grabbing toys, right? You know how they are. They don't just sit down and play with one thing. So the more kids that come in the room, the more toys are going to come off the shelves. But if you have just a slight increase in the number of kids, you're going to have a much bigger increase in the number of toys, right? Because each one is probably pulling 10 off the shelf. This is an example of a direct variation. It's not one for one. Each toddler does not take one toy. Each one probably rips 10 off the shelves. And so you're getting toys thrown out on the floor a lot faster than the toddlers are entering the room, but they are going in the same direction, right? So we call that a direct variation. And we write a formula, and in this example, it would be the number of toys on the floor of the room is equal to the number of toddlers times a constant that we call K. Now, I think it's cheesy that we use K to stand for a constant, like constant. It reminds me of Toys R Us, how they had the backwards R. But, Toys R Us is history now. I think it was that bad grammar that got him in trouble. And so what we can do is we can simplify this to sort of a generic formula that looks like this. Okay? One thing is related to the other thing with some sort of constant to keep them in place. If every toddler took 10 toys off, our constant would be 10. All right? So that constant will make sense. Let's look at a problem that explains this. Example 60.1 illustrates this. The number of boys in every classroom of a school varies directly as the number of girls. Now, when we're writing down the equation, we can write it down just like the sentence says. The number of boys in a classroom varies directly as the number of girls. I just wrote it down exactly the way it was said to me. Don't overthink it. Just write it down like the sentence says. In one room, there were 8 boys and 2 girls. If there are 5 girls in another room, how many boys are in this room? Okay? This is the way these problems always work. They're a two-step problem. First, John gives us a scenario that tells us about the two variables. This is how we're going to use this data to calculate the constant. Then, once we have the constant, we'll use that in the second part of the problem to solve for whatever we're missing, like in this case, the number of boys, right? So let me show you how that works. Here's our formula. Here's our first scenario. So we can write 8 equals K times 2, right? Number of boys, number of girls. K is the mystery that we have to figure out. Solving is super easy. We'll just divide both sides by 2, and we find out that K equals 4. So the constant that relates these two variables is 4. Now we can use it here. We pay attention to our equation again. The number of boys equals the constant 4 times the number of girls, 5. So the number of boys in that second classroom is 20. Oh, that's pretty easy, right? Two scenarios. One allows us to calculate K. The other one allows us to answer the question. Okay? Now, let's try one that is slightly more confusing because instead of it being like a normal everyday girls and boys in a classroom thing, it's going to have a physicsy kind of vibe to it. Oh no, I don't want to do it yet because this one is the other kind. Okay, let's talk about inverse variations. Okay, imagine this. Imagine a room with tables all around the edges of it, and all of the tables are full of open boxes of pizzas. Okay, they're all sliced up and ready to go. Nice and steaming hot. The whole room just is baked in the smell of pepperoni. And a steady stream of teenagers enters the room. I'm going to say teenage boys because teenage boys have an ability to eat pizza that I think most teenage girls don't even want to have. Imagine that these boys start walking in this room one at a time. Now, every one boy is going to eat more than one slice of pizza. Again, I don't know about you guys, but I know a lot of teenage boys that can eat, let's say 8 slices of pizza. 8 full-size slices of pizza without even blinking. So what's happening is that our pizza is disappearing before our eyes because as the number of boys increases, the amount of pizza that we have is decreasing. Okay? This is called an inverse variation because as one thing is going up, the other thing is going down. Okay? It's similar to that, excuse me, Gracie's crying. Hang on. Do you want to go out? She smells food in the other part of the house, so she wants to go. See about that. The same idea is happening as with our toddlers and toys in that it isn't a one-to-one relationship because one boy does not eat one slice of pizza. The pizza is disappearing at a faster rate than that, and that's where that constant comes in, right? That's the number that connects the two things. So it's similar to the other one, except the things are moving in opposite directions. So now what we have to do is change our formula just a little bit. A equals K divided by B. Okay, so in this case, it would be the pizza available equals the constant divided by the number of boys. Right, excuse me. Again, you don't have to overthink this. The sentence will allow you to relate those two. Hang on just a second. I better see if she's stealing food. Students. She was trying to eat cat food. Oh my gosh. Okay, so notice how it's different. For an inverse variation, we divide by the other one. Okay, so now I'm going to do example 60.3, which is another everyday life one, except it's got clowns, so I'm sorry. The number of clowns was, oh, sorry. Never mind. Let's do 60.2. 60.2, the number of revolutions per minute varies inversely as the number of teeth in the gear. What? It's physics. This is frightening me, but I'm going to pretend I don't care. The number of revolutions per minute, so that's our first thing, revolutions per minute, is inversely related to the number of teeth in the gear. T for teeth. This is just one thing. We can just call it plain R if we want. So the number of revolutions is inversely related to the number of teeth. Now we're going to have two scenarios. If 40 teeth results in 100 revolutions per minute, what would be the RPM if the gear had 30 teeth? We do not have to understand the physics of this or even think about them. I cut those letters out because I don't want it to look like we're multiplying three things together. We'll just let that stand for revolutions per minute. So we do it exactly the same way we did the other one. We use the first set of scenario to solve for k using this. So 100 equals k over 40. We cross multiply and we get k equals 4,000. Huh, okay. And now we're over here and we say that the revolutions that we want to figure out, we're using the same thing, equals 4,000 divided by 30. You can do the division on that, but I'll tell you right now, it's 133 and 1/3 revolutions, and we can put revolutions per minute if we want. That's the right answer. Okay. The last problem, which we will do, goes back to the direct variation. Sorry, I got spun around. I meant to do this 1 second. The number of clowns was directly proportional to the number of performers. Okay, directly. So clowns equals k times performers. If there were 40 clowns when there were 20,000 performers, how many clowns would there be if there were 12,000 performers? Okay, two scenarios. Here we go. 40 equals k times 20,000. Okay, this is a little weird. Hang on, my dog is going crazy. Back you go, back you go, back you go. Now I understand. There's a pan of freshly baked brownies in the kitchen and it smells quite delicious. Okay, we divide by 20,000. This, divide by 10, 4 goes into 20. I see that k equals 1 over 500, right? That would become 5, and there's 2 zeros left. 1 over 500 is our constant. Oh, that's weird. We haven't had one before that is a fraction, but it's okay. It's fine. So now we want to find out how many clowns are there when the performers are 12,000. So we want to go 1 over 500, because that's k, times the performers, 12,000. Okay, let's divide by 100. How many times does 5 go into 120? 24 times, right? So C equals 24 clowns. Again, I like, if there's words in the problem, I like a word in the answer, and that's right. Okay, direct and inverse variations. There's the formula for the inverse. There's the formula for the direct. It's always a two-step problem where first we solve for k, and then we use k to answer the question in the second scenario. Yay, we're done. Goodbye.